I'm Will Byrd. Welcome to, I think it's the 5th annual miniKanren and Relational Programming Workshop, co-located at ICFP in Seattle. And I welcome you on behalf of myself and my co-organizer, Nada Amin, who can't be here unfortunately, and the program committee. Thank you for coming, either virtually or in person. And we've got some very interesting papers, research papers. And also at the end of the day, we're going to have a discussion on the future of miniKanren and relational programming, which directions might be interesting to go and where we should focus our research and implementation efforts. It's a small community, so having some sense of direction I think is important. Many of the people in the community, even though it's a small community, it is, I think, bigger than it looks in that there are people around the world doing research, especially the group, Dmitry Buchalov's group from St. Petersburg State University has a large group, in addition to people from Indiana University, Dan Friedman students, of which I'm one. And there are other people who've learned about logic programming and constraint logic programming, relational programming through miniKanren and through Jason Heeman's microKanren system, for example, through implementing that. So we do have a bigger community than it might look, but it's hard to get everyone together at once because we're in Japan and Russia and all over the world right now. So welcome now and later for people watching recorded YouTube videos. Today we're going to start with a miniKanren tutorial. Now, it's a little tricky for me to give miniKanren tutorials to an audience like this because I've probably given 500 miniKanren tutorials. I'm not sure. I gave one yesterday to someone. And the part that's tricky is that we have some people in the audience who maybe haven't heard of miniKanren. And we have other people in the audience who've implemented miniKanrens and written PhDs on miniKanren. So I think what I'll do is I will give sort of my standard introduction to miniKanren. I introduce the language and show some of the interesting things, or at least what I think interesting, that we can do with miniKanren, in particular writing an interpreter for a subset of scheme in a relational style, and showing some of the neat tricks that we can do with that. And from that point, I think because we do have an audience here of people who are experienced with miniKanren, I think I'll open up a little bit and try to make it interactive. And so if people would like to talk about aspects of miniKanren or want to try implementing something, we could try doing something a little more dynamic because we do have a bunch of people who have expertise in miniKanren. So if nothing else, it could become a little more of an open session or a Q&A or talking about aspects of miniKanren that maybe you're aware of but haven't had a chance to talk to, between the people in the audience today. We actually have a fair number of papers on miniKanren and research projects and implementations and things like that. So I think there's lots of expertise in this room, so we can make it interactive. Okay, without further ado, I've got about an hour, 22 minutes. And so we'll begin with the basics of miniKanren and what is miniKanren and why might you care about miniKanren or relational programming, and then we'll go into the details of how to write miniKanren programs. So the first thing I'll point out is that miniKanren is usually, although not always, viewed as an embedded language. So in this case, we're using the scheme programming language, which is a variant of Lisp, as the host language. So you can think of miniKanren as an extension to the scheme language. Scheme, like most Lisps, has a very powerful macro system that allows you to extend the syntax of the language. So if you have a version of Lisp that doesn't have a for loop, you can add a for loop. If you have a for loop in the language and you don't like the way the for loop works, you can change how the for loop works. So we take advantage of that in miniKanren to add syntax to the language, to the scheme language for logic programming, or in particular constraint logic programming. And we'll talk about what that is. But the first thing to understand is the reason I'm starting SHA-Scheme is that we're going to extend SHA-Scheme with some primitives. Now, Scheme is a Lisp, and it is a multi-paradigm programming language, but is often used for functional programming. And if you're not familiar with Scheme, I'll show you just a few examples of Scheme, so you get used to the syntax and to how it works. Here we're in an interactive session of what's called the REPL, the read eval print loop. And so I can write things like +2, 3, and get back 5. By the way, is this font large enough for people? I can make it larger if you need it. Is it okay? All right. You can also sit up. We have some open seats, so if you need to move a little closer, it's possible. Okay, so you can see that in Scheme we have what's called prefix notation. So we have parentheses that denote a procedure application or application, and then in the first position of the application we have the operation, the function that we're going to call. Okay, so here if I want to add 2 and 3, I just write left paren plus 2, 3. 3 is an expression that evaluates to the value of 3. It's a self-evaluating expression. The first expression I typed in, left paren plus 2, 3, right paren, that is also an expression that evaluates to the value 5. So in Scheme we have expressions and we have values. There are a few other things that I'm not going to talk about in Scheme, but for our standpoint we can think of expressions and values. Now, what I just showed you isn't really miniKanren', because in miniKanren' we have to deal with addition in a particularly careful way that in most programming languages you don't have to deal with. Okay, so I'm going to be careful to try to show you things that are purely miniKanren' from now on, but I will show you 1 or 2 more things that will pop up later that are worth showing you. So first of all, we're at the International Conference for Functional Programming, so probably most people here know something about functional programming. Most functional programming languages, traditional functional programming languages that we see here, are based on the lambda calculus, Alonzo Church's lambda calculus, and most functional programming languages and many sort of more traditional mainstream languages such as Java and Python and C++ support something called lambda. So I can write a lambda expression in Scheme like this. So this is saying I am going to create a representation. This is an expression that represents, there's a lambda expression that evaluates to a procedure. Okay, you can think of that as a function. There's a function that takes one argument called x and then adds that argument to itself. And if I evaluate that lambda expression, I get back a procedure, which is an opaque object. I can apply that procedure to, say, a number, the result of adding 3 and 4 by wrapping an extra pair of parens, because parentheses in Scheme mean procedure application, with the exception of something like the lambda form itself. So we have special forms, there's a syntax, and otherwise every pair of parentheses means procedure application. So here we have a procedure that will take a single argument and add it to itself, and that will be applied to the value of +3, 4, which should be 7. And sure enough, we get 14 back. Okay. And I'll show you one other thing of Scheme that's important to know. In Scheme, we have lists. And so we can say list 3, 4, 5. Okay, so the list function, when it's called with a number of arguments, will construct a list. And of course, we can have expressions in those argument positions to list. Okay, and we can create a list like this. We can also create a list using quotation. Okay? And a quote turns out to be extremely important in list programming. So quote of any datum is just datum. So quote of the list 3, 4, 5 evaluates the list 3, 4, 5. we'll see this quite a bit in the future. And in particular, notice that there's a big difference between something like plus 3, 4, which evaluates to 7, that expression evaluates to 7, versus quote plus 3, 4, which evaluates to a list plus 3, 4. One other thing that you should know is that to create lists in Scheme, there's a more primitive mechanism than calling list. So in Scheme, there's something called the empty list, which is usually written as the expression quote empty parens. That's the empty list. And then to build up lists, we use something called cons. So I can cons 3 on the quote empty list to get the list 3. And I can cons 2 onto that list to get the list 2, 3, and so forth. If I want to get the first element of a list, I can take the car of that list, car, which sounds like a strange name for an operation. You can think of this as first or head of a list, and some languages are called first or head. Car is a historical name. The history is very interesting. I won't get into it though. So car gives you the first thing in the list. Coulter gives you the rest of the list, the rest of the elements of the list. And I'll just show you one more thing. And so I'm basically giving you a crash course in Scheme. The other thing you should know is that internally inside of Scheme, there's something called pairs. So you can think of these as a memory cell that contains 2 pointers in memory, if you're familiar with pointers in memory. And so we have the car pointer and the Coulter pointer. In this case, the car of the pair is just the concrete value 3, the atomic value 3, and the Coulter is the atomic value 4, but we're allowed to cons up things that are more complicated. So I could say cons 2, 3 onto cons 4, and you can see we have this nested tree-like structure. And so the car pointer is pointing to another pair, which has 2 and 3 as its elements. And I can do things like take the car of that value and get 2.3. And if I want to, I could take the Coulter of that value. And the last thing you need to know about Scheme is that you usually won't see these dots in what's called a proper list. So, if I cons 3 on the 4, you see the dots, 3.4. But if I cons 3 onto cons 4 onto the empty list, you don't see the dots. You see 3.4. But I can assure you that the dots are there, they're just hidden. So that's actually 3.4 empty list. So I can just quote that whole expression, and it prints out as the list 3, 4. And the reason the dots are suppressed is that it can get tedious to read dots when you have complicated structures. Okay? So that's it. That's all you need to know about Scheme. We've seen variables in the form of lambda. We've seen application and lambda and procedures, and also quote and lists and pairs. Okay. All right. Any questions so far? Okay. So now I will introduce. So I'll do this a little backwards than how I do it sometimes. I'll introduce the core parts of miniKanren. Okay. And then we can take a little break and talk about why we've seen this little language and what we might use it for. So notice I'm also not justifying why I'm showing you these operators in Scheme, because most of us here are familiar with functional programming. We understand why there might be a use for lambda and application and so forth. But of course, people who have never seen functional programming are going to be mystified by this. So I'm going to show you a couple of operators that are similar. I mean, this is logic, constraint logic programming. So it's not exactly functional programming, but once again, just like we can have extended lambda calculus, we're going to have a few operators which are useful for constraint logic programming. So I'll introduce those operators and give a couple examples, and then we'll take a step back and talk about why we might use those and how to think about those programs that we can write as opposed to the way you would think about functional programs. Okay, so we're done with Scheme. I'll get rid of Scheme. And I'm going to start Scheme again. So we're back in Scheme, but we're going to pretend we're not in Scheme. I'm just going to load miniKanren'. Okay, so I'm using an implementation called Faster miniKanren' that was created by Michael Ballantyne, building on prior work from other people, and at this point, other people have also contributed to it, but to load the version in Scheme, I have to do this magic incantation. Okay, so now we have extended the Scheme language with miniKanren'. miniKanren' has 3 core logical operations. The first and most important logical operation is equal equal, which is a type of equality operator which is implemented using something called the unification algorithm. And you may have heard of the unification algorithm in terms of artificial intelligence research, or maybe in terms of type inference or things like that. Okay, so unification algorithm comes up in many guises. It comes up in automated theorem proving and so forth. Okay, so what does this operation do? Well, it takes 2 arguments. And so the syntax for it is, whoops, I can say equal equal T1 and T2. So that's what a use of equal equal looks like. So T1 and T2 are what are called terms. So terms are kind of like values in Scheme. So values we're used to, so things like lists and numbers and booleans and so forth. But we're going to have one other feature, which will be what are called logic variables, a special type of variable, which really is more like a special type of value, can also be part of a term. So we'll see that in a minute. But you can think of, from an analogy, of equal equal as like a form of the equality check in most programming languages. So in a language like most Lisps have an equal question mark operator to tell if 2 values happen to be the same. Equal equal is the metaphorical equivalent in constraint logic programming. Now, I could write something like equal equal 5 5. Now 5 and 5 do have the same value, but instead of saying that equal equal 5 5 is true, like we might in functional programming, we say that equal equal 5 5 succeeds. So instead of talking about true and false, we start talking about succeed and fail. Now, if I run this equal equal 5 5, if I try it out, I don't get back succeed, I get back a procedure. We've already seen a procedure before when we're in Scheme land. A procedure is what we get back from evaluating a lambda expression. So under the hood, I'm sort of leaking something about the implementation of Faster miniKanren'. Under the hood, there's some Scheme functions flying around, but we can ignore that. However, because Scheme doesn't know anything about miniKanren', we have to have an interface between functional land and miniKanren' land, or if you can think about Scheme land and miniKanren' land. Okay, so somehow we have to have a way for Scheme to interact with miniKanren', and the way that is something called run. So run is our interface operation. So I said that there are 3 core logical operations. That's true. And there's also one interface operator or syntax, and that's run. And so run is syntax, a special syntax. It's a macro. And in this case, I'm saying I would like one answer, if it exists. And I have this Q thing, which is what's called a query variable. And then we have the body of the run, which is equal equal 5 5. So one way to think about this is we're asking a question: for what value of Q is it true that 5 is equal to 5? Now, that's one way to think about this metaphorically or philosophically. For which value of Q is it true that 5 is equal to 5? And the answer is for any value of Q. For any value of Q, that is true. That might sound like a strange question to ask, but as we get into more interesting questions, I think you'll see why we ask these sorts of things. And we get back this baffling answer. We get back a list of length 1 that contains _.0, which is a Scheme symbol. It's a symbol. Okay, what could that possibly mean? What that means is that we have a representation of our query variable q, and this is a representation that q remains unassociated. It doesn't have a value as part of this computation. And in some sense, what that means is that q could represent any value whatsoever. So the answer to our query or question is that q could be any value. And for any value of q, it is true that 5 is equal to 5. Okay. Now, let's ask a slightly different question. Okay, so now we're asking the question, for which values of q is it true that 5 and 6 are the same? And so for which values of q is that true? That 5 and 6 are the same? No values, okay? So we get back the empty list. There are no values of q for which 5 and 6 are the same. It becomes a little more interesting if we involve q in the computation itself. So now we're asking the question, for which values of q is it true that q and 6 are the same? And in this case, obviously, well, when q is 6, then q and 6 are the same. Okay, so these are simple sounding questions. Let's make it a little more interesting. So we could say, how about this? For which values of q are q equal to q? Well, for any value of q. So we get back the answer we saw previously, this _0. All right, let's try to make it a little more interesting. What about this question? For which values of q is it true that q is equal to the list containing q? Now, what should we return in this case? I don't know. In miniKanren, we decide that we return the empty list. We say there is no answer. There is no q such that q is equal to list q. So our version of equal equal implements what's called the occurs check. So if the variable q that we're unifying with this other term, if the other term contains q, it's not equal to q, but is a structure containing q, then we say there is no answer, because in order to have an answer, q would actually have to be infinite. We would have to have an infinite term or an infinite tree in order for q to be the same as list q. And so we have decided to make that illegal. I should point out in some logic programming or constraint logic programming languages, this decision isn't made because it's expensive to implement. It's expensive to do this check. So in many logic programming languages, they just don't do the check. And then furthermore, so like in Prolog famously doesn't do this check. But in other languages like Prolog 2, they say, oh no, that's okay. It's okay to have infinite terms. Okay. In fact, there's a version of miniKanren that people have played with where you are allowed to have infinite terms. They're called infinite rational terms. And you're allowed to get an answer back. So just like in Scheme, you're allowed to create circular data structures. You're allowed to have a list whose car or cooter points back to the list itself. Okay, so you're allowed to do that in Scheme. You can also be allowed to do that in this logic programming, but we don't make that decision. Okay, so everything you see about miniKanren, if you're thinking of it from a research standpoint, you should also be thinking, for every decision that miniKanren made, what would happen if you did it differently? Okay. So we could make this a different choice, but we've decided, at least in the standard version of miniKanren, to enforce this occurs check. Okay, but it's not the only choice you can make. All right, and then, okay, so let's make this a little more interesting. Let's introduce another one of the 3 logical forms in core miniKanren, which is called fresh. What fresh lets you do is introduce locally lexically scoped logic variables. Now, we've already seen a logic variable. As our query variable q is a logic variable. Here we also are introducing x and y. We are allowed to refer to x and y within the body of the fresh. So one way we could do this is we say q is equal to the list xy. Now in this case, we are saying that Q has some structure. It is a list of length 2, but we're not saying what's in that list. So if I run that query, I can see that we get one answer back, and that answer is itself a list. So we have a list of answers, contains one list of length 2, and our representation of x, the logic variable x, is _0, and our representation of y is _1. If I make the list a little more complicated, I could put another x in there, and we see that the numbering gives us another 0. And that's because the numbering of the zeros and ones refers to the distinct logic variables that don't have values at the end of the computation. So x has the numbering 0 because it's left to right in terms of the answers. Y has the number 1, and because we have 2 x's in that list, you can see that we have 2 zeros. Now, we also can add more than one equal. So here we have one use of equal or unification, but I could also add another one. And this is a conjunction or an and. So I could say, not only is Q equal to list x, y, x, but we also have the case that x is 5. And so in this case, we can see that our result is a single list where in the x position we see 5 both times. For y, the number has changed. It went from 1 to 0 because we always renumber our answers from 0 to 1 to 3, 2, 3, so forth, from left to right when we have a variable that hasn't had a value associated with it by the end of the computation. And of course, if I wanted to, I could give y a value. Now, I could give y a value like 6, and it would work as you expected. But I could also do something like, say, y has the value of x. Okay? And that might look like an assignment. These might all look like assignments, but they really aren't. They're more general than the sort of assignment or a let binding that you're used to. So first of all, we don't have mutation. So it's more like a let binding in functional programming. But it's not really like a let binding in a way, because we're allowed to reorder these expressions any way we want. And so, and in fact, we don't ever have to give concrete values to x or y or q if we don't want. In this case, we're saying that x and y have the same value, but we're not saying concretely what they are. So we can see that we have a list of one answer, which itself is a list of length 3, and our representations of x and y are all underscored at 0 because even though x and y are all what we call fresh or unassociated logic variables, because we've tied them together by unifying x and y, they get the same number. And if I were to associate with either x or y with a value, say make y is 7, then we would see that same value repeated. Importantly, we can reorder any of these conjuncts, and we can also, within a single call to equal, we can reorder, we can swap those arguments, okay? All right, and the program still has the same meaning, has the same declarative meaning. So this is a form of declarative programming. So we've now seen 2/3 of the logical language and 3/4 of the core language. And we're going to have one more thing that I'm going to show you for the core language, which is the ability, you could think of it as the ability to make choices, but it's not really the way to think about it. It's not so much the ability to make choices as it is the ability to collect multiple answers. So, and that is an operation called cond, which syntactically looks something like McCarthy's cond operation. Okay, it's sort of metaphorically inspired by cond. And so the simplest version I could show would be something like this. All right, so in this case, we have a cond expression. E stands for every. We're going to collect every, or try every clause. And we have one clause where we say Q is 5, and another clause where Q is 6. Now, if I were to hit return, what we see is a list of length 1, In this case, it happens to have a 5 in it, so we got Q is 5. Now, I could also ask for more than one answer, so I could say, give me 2 answers. In this case, I get a second answer from the other Kandi clause, which is 6. I could also ask for 10 answers. In this case, there are only 2 answers. It can be annoying to have to guess the number. So if you want all the answers, we have a shorthand, which is just saying run star. You have to be a little careful with run star because you can get infinitely many answers from miniKanren. But you also have to be careful by putting, when you put in a concrete number, because it's also possible that there are only 2 answers. And if you ask for 3 answers, either you will get back 3 answers or your program will go in an infinite loop, which we will see. Okay, so that's a way to make choices. And in Kandi, we're allowed to have more than one what's called a goal expression. Goal expressions are Kandis and freshes and equals. You're allowed to have more than one goal expression within the Kandi. So I could do something like, say, x is 5, y is 6 in this one. And then here I could say y is 7. And I could also, within my fresh, because that's a conjunction, I could say q is equal to the list x, y. So in this case, this program, which is starting to get a little more interesting, q is going to be a list of x and y, and we have a choice here. In one case, x is 5 and y is 6. In a totally distinct case, which has nothing to do with the first case at all, y is 7. So if I run this, I will see 2 answers. So I see that q is either associated with the list 5, 6, or it's associated with the list _0, 7. If I wanted to, I could reorder the Kandi clauses. So I could say, okay, I want to swap these 2 clauses, and I get back the same list of answers, but with the answers in a different order. Okay, so you can think of these sort of as a set. You can get a little trouble if you think of it strictly as a set, but if you write your program to be non-overlapping, you can think of the answers sort of as a set. We can also do sort of more aggressive reordering. So we could make the Kandi come first. I can swap the equal calls within an individual Kandi. And my program will still have the same behavior. I might get the answers back in a different order, but I will still get the same answers so long as those answers exist. If I ask for 3 answers or all the answers, and it turns out there are only 2, my program could either give me a list of length 2 or it could go in infinite loop. So those are sort of the choices. One way to think about Kandi is it is a disjunction or an or of conjunctions. So we have 2 choices here for the Kandi, and within each Kandi clause, all of those goal expressions all the goals have to succeed. Okay, so that is the basic logical operators of miniKanren. Now you can see that we're inheriting a little bit from scheme because we do have numeric constants. Okay, so we have 5 and 6. Those are inherited from scheme, and we're also piggybacking on the fact that scheme has lexical variables. So this fresh x, y, and the q, those are actually scheme variables that we're sort of repurposing. We're binding those to our own internal representation of logic variables. Okay, so we are using part of scheme. And another thing from scheme that we can use is define. So I will show you sort of the hello world example, which is very common from, this is basically the hello world example of logic programming, which any Prolog programmer will have seen. So here we're reusing define, and we're actually reusing lambda. Okay, so we're saying we're going to define a function called appendo. By convention, we end our relations. This is a definition of a mathematical relation with an O. That's due to Dan Friedman. There's a long story behind that I won't get into, but makes it sound kind of like Italian or Spanish or something. So this is Appendo. And Appendo is a relation that takes 3 arguments. So we take 2 lists, L and S, and L plus S, our third argument, is going to be L concatenated with S, or L appended with S. That's going to be our 3 arguments. I think most people here probably have seen append in some functional language, so I'm not going to go over that version right now, but I'll just show you what the miniKanren version would look like. So we want to have more than one choice. Appendo is going to be recursive. So one thing we have to have is a base case. In the base case, if L is the empty list, then we have to associate some value with L plus S. You can think of this metaphorically as the return value in the functional version. So in this case, I will say that L plus S is equal to S, the second argument coming in. Okay. So that is our base case. Now, this already is a working relational program, and if I wanted to, I can run this. In fact, might as well. Okay, so it's okay to have a conD that only has one clause. So I could say run one Q, appendo empty list to list ABC to be Q, and then sure enough we get back ABC as the argument, the third argument position. Okay, so we can already start testing things out. Let's go ahead and add the recursive case to complete it. In this case, we're going to need some placeholder variables. So I'm going to introduce a fresh, which I'll fill in a minute. And here, we're going to check to see if L is the pair of AD, that's a convention, or it's like first rest, or however you want to call it. So we're going to need 2 logic variables, A and S. If that's the case, then we're going to append D onto S to get some partial result res, and then we're going to associate our output argument, L plus S, with the result of consing the first element of A onto res. Okay, so if you've ever written append in a pattern matching style, this actually is reminiscent. Okay, so probably a little easier to see as pattern matching. Now, if you haven't seen miniKanren before and you're seeing conD and equal and fresh for the first time, this might look a little bewildering. We've got plenty of tutorials on miniKanren.org and books and theses and all sorts of things, videos that describe how to write this sort of program in great detail. I'm not going to talk about that right now. What I really want to do is show you kind of how these programs feel. Okay, but we can see at a high level on the outer part of the program we have a conD. We're making a choice. The first clause isn't recursive. We're just doing these sort of equality constraints. And in the second clause we have this recursion. So we're basically breaking apart L. We're destructuring L, and then we're putting together the results of the recursion with the first element of L, and saying that's the third argument, which you can think of as the output. Okay, so now that I have appendo, I can go back to my run query. Okay, so this should still work, sure enough. I can still append the empty list to ABC, but now we can start doing more interesting things. So I should be able to append AB to DC, okay, and that works the way we would hope. Now, if that were the end of the story, wouldn't be very interesting because these are things we're used to doing with functional programming. However, the part that's interesting is that because we've written appendo as a relation, there's no distinction between the first 2 arguments and the last argument. In functional programming, we have this distinction between inputs and outputs. The whole idea of relational programming is we're erasing that distinction. They're just arguments. It doesn't matter. Okay. Now, in this case, we can say the output should be ABCD. And in this case, we see that our query variable remains unassociated. So this is showing that we have consistency, that appendo of AB, DC, ABC, AB, DC, AB, DC, yeah, is consistent, okay? Now, I could change the answer and throw in an E, we get back the empty list instead of the list containing a reified version of Q. So here you can see that we have the three arguments are not consistent. Okay, it's not that the answer is wrong. You shouldn't think in terms of answers or outputs. You should just say that this relation does not hold. We have a three-place relation. The relation holds when we have AB, DC, AB, DC. And the relation doesn't hold when we have AB, DC, AB, DCE. That relation doesn't hold. So you can think of this in terms of maybe a giant database table or just a giant data table. We're writing down metaphorically every triple, every three lists that go together, where the first two lists appended together are equal to the third list. So you can imagine writing down that table, and in a sense, we're just doing a query over that table. The table just happens to be infinite. So this is sort of like a database lookup. It's just our database is infinite, and because it's infinite, we have to construct the table during computation time. We can't just actually create the full table and look at it up. Now, the more interesting things we can do is we can do what people often refer to as running backwards. So we could say, all right, if we were to append AB to some list Q, which we don't know, and the two appended together should be ABDC, what must that second list be? In this case, we can find out that it's the list DC. We can also go further than that. We can say what two lists, X and Y, appended together will give me ABDC. And here's one answer. So I've asked for one answer with my run one, and I can say the empty list appended to ABDC would give me ABDC. I could also ask for a second answer. So give me two answers, and in this case you can see that the second answer is the list A and list B, DC. And in fact, let's see, there are three answers, great. Four answers, great. Let me just format these. Okay. All right, in fact, there are going to be five answers in this case. And sure enough, we get five answers back. Now, the interesting thing here is what happens, there are exactly five answers. What happens when I ask for six answers? One of two things will happen. I will either get back the five answers I've already gotten back, or I will get back an infinite loop, which is not coming back at all. Let's see what it is. All right, I think we know the answer now. The answer is infinite loop. There is no sixth answer. And in miniKanren and in Turing complete logic programming, constraint logic programming in general, it is, in general, impossible to tell there is no answer from infinite loop. Because what miniKanren is really doing is it's doing a search. It's doing a search to see if it can find any answers. And the search space includes all possible lists. Because there are infinitely many lists, it's possible that the search will just keep looking forever, even if there is no answer. So that's the case we have here. Now, in the particular version of Appendo I wrote, we can do better. And the reason we can do better is that miniKanren, like most constraint logic programming languages, has sort of an Achilles heel, has a problem. And the problem is that our conjunction, our and, isn't really commutative. I have to put an asterisk when I say that our and or conjunction is commutative. It is true that I can reorder these clauses, and the program has the same declarative meaning. Okay, the program means the same thing as I reorder these goal expressions. However, it means the same thing modulo a certain claim, which is, right way to put it is, if I do a query and I ask for n answers, and there are n answers, I will, in theory, get the n answers back. Now, I might need, giant amounts of memory and time, might need trillions of years to run the query, but in theory, the query would return. However, if an answer doesn't exist, then one of two things will happen. Either I will get back a smaller number of answers, maybe 0, in a finite time, what's called finite failure, or the program will go in an infinite loop or diverge. And there's no way in general for me to tell those two apart. However, as a general rule, you want to put the recursive calls at the end of the conjunctions. Now, Jason Heeman and Michael Ballantyne, I believe, are working on an optimizing compiler that might be a little smarter about some of these things. Or you can imagine doing a rewriting of your program or whatever, or static analyses or dynamic analyses or whatever, to try to tame this problem a little bit. Okay, certainly this syntactic transformation you could do automatically. The problem is when you have multiple recursive calls, there's no way to put them all last. Okay, you could, and it turns out that depending on the arguments coming in, you might prefer one recursive call ordering versus another recursive call ordering. So that's kind of the bad news. So I may as well tell you the bad news up front. In this case, if I reorder the goals, like this, so the recursive call comes last, then I have no problem. So I can do a run star, everything works beautifully, and so I can fill in the gaps. And in particular, probably the most interesting thing to me isn't really when you're running it backwards, but when you're doing things like this. So I can also write this sort of program. We haven't talked about quasi-quote and unquote, but this is another type of quotation. In Scheme, this is saying I have the list that begins AB, and then the continuation of that list, or the rest of the list, is represented by the logic variable x. It's an unknown. So I could say, if I have a list that begins with AB and has something else in it, maybe, either nothing else, that could be the empty list, in which case the whole list is AB, or it could be arbitrarily long, appended to some list y, and to get A, B, D, C, what would x and y be? What are all the choices? And in this case, there are two choices. There are three choices, actually. Okay. All right, there are three choices. So either x is the empty list and y is list DC, or x is the list D and y is the list C, or x is the list DC and y is the empty list. Okay, so this to me is the most interesting case of all, because you can imagine what's called function inversion. If you just want to run your functions backwards, you could invert the functions, and there are techniques for trying to invert functions. And you would have a version of append running forward, a version of append running backwards. But the interesting thing to me is that here we're not inverting the function. There's no way you could invert the function to get this sort of behavior. Rather, we are allowed to have terms. I said that unification operates on terms. And here you see a term that contains a logic variable, but it's partially ground. Okay, so we're allowed to have terms in any position that contain logic variables, but also have some structure. So to me, this is the interesting part of relational programming that sets it apart from other styles of programming, is that we're allowed to write this sort of thing. So we're allowed to put holes representing unknowns anywhere we want in any arguments at any time, and it still works. And this also means that every problem in miniKanren can be thought of as a synthesis problem. Everything is a program synthesis problem in some sense, okay, if you want to think of it that way. So that is kind of the core of miniKanren. Now, I want to jump from append to sort of our most fun example, which is the classic, now classic relational interpreter. So I am going to, okay, so first of all, yeah, that's fine. So let me load Actually, I'm going to jump to the full version right now. Okay. Okay, so if you're familiar with functional programming, you've probably seen or likely written an interpreter for a little functional language or for lambda calculus or something like that. So what I've just loaded is an interpreter for a subset of the scheme language. So you can think of this as an extended call by value lambda calculus, if you know what those terms mean. And the way we're going to use this interpreter is by calling the evaluo relation. So if you have an evaluator, normally with your evaluator, you would take an expression, evaluate it to get a value. But here, because we don't have a distinction between inputs and outputs, we just have expressions and values. So if you want to think about it, our evaluo takes an expression and it takes a value, and those are related. So the expression has this value, or that value matches up with that expression. Okay, so that's the way it's going to work. So a simple example of this, if I want to, quote, run it forward, would be something like miniKanren'23. And so you can see that if I evaluate this expression, notice I quoted this. Okay, so this is not being evaluated in scheme, this is evaluated in miniKanren by the evaluo interpreter. So if I evaluate this cons call, I get back the pair 3.4 as the answer in miniKanren, because I'm writing an interpreter in miniKanren that's a relation. Okay, now the interesting thing here is I can now, in this case, run it backwards. Okay, so we'll start with the running backwards example. So I can go the other way. I could say, if I know the value is 3.4, what is an expression that evaluates to that value? And if I run it, well, first of all, I can see I can quote 3.4. That's one way to get 3.4. But let me ask for a second answer. And here I can see the expression cons 3.4. That is an expression that evaluates to 3.4. And I could ask for more. I could say, give me 99 expressions that in a subset of scheme evaluate to 4. And sure enough, I get some more complicated expressions. So here's one that looks weird. So let me try to understand what this is saying. Oh, well, okay. A lot of these I would never come up with, okay, on my own. So this is saying, I'll rewrite this slightly to make it a little easier to read. This is saying that you can have an application of a variadic lambda, a procedure that takes any number of arguments, basically, is what we're going to end up with getting from this lambda expression. Take any number of arguments, ignore them, and then return the value of, quote, 3.4. And what are the arguments? Well, because list happens to be in the interpreter, list happens to be a nice variable. And so we're getting the variable list that's bound to a procedure that creates lists as 3 arguments being passed into this function. And if I evaluate in scheme, sure enough, I get 3.4. Okay, so those are the sorts of things where now I'm writing the programs backwards. And let me just show you a fun example of how you can push this a little bit, which is if I want to evaluate something more complicated, so I can say, I want to evaluate a more complicated expression. Now this version of the interpreter has LUTREC, so we can write recursive programs. So I can define append. Okay, notice this isn't appendo. This is not miniKanren append. This is, honest to goodness, scheme append. This is a regular functional programming append. So if I define append the way you would normally define it in a functional language, like that, and then I can, let's see, uh-oh, I think I fat fingered it. Hold on a second. try this again. Okay, so I can say the output is Q, and we want a letrec append of lambda ls, and we're going to use an if. If L is empty, then we're going to return S. Otherwise, we're going to cons the first element of L onto the recursive call of the rest of L to S. Okay, and now I can make a call to append. Now I've defined it, and I could say we're going to append AB to CD, and we'll see what we got back. All right, and sure enough, we get A, B, C, D. So what I've done here, it's a little sleight of hand, it's easy to miss it. I've written an interpreter in miniKanren as a pure relation that can interpret a subset of scheme, including recursion and so forth, lists and so forth. So I can just put in scheme code. Okay, in fact, I'll prove it to you. I'm not. If I took that letrec and I just ran it in scheme, I would get the same answer back. Okay, so this literally is just scheme code. So I wrote a standard interpreter for scheme, but I wrote it in miniKanren as a relation. So we can evaluate scheme like normal going forward, but that's not very interesting. So I will take the output, the value that you would expect to get back. And so first of all, we can see that our answer is consistent. If I have append defined with that call, then sure enough, I get back A, B, C, D. But the interesting part is now I can start putting logic variables inside of the append code. So for example, if I put the Q, I have to put a comma Q here, this is all quasi-quoted, but basically now I put in a whole represented as a logic variable, saying this is a value I don't know. Okay, this is an expression I don't know. And if you completed it, if you completed that expression, then under a scheme interpreter, it should give you A, B, C, D. So if I ask for one answer back, then sure enough, I get back the list AB. If I try to get a second answer back, I see something interesting, which confused me and confused Michael Ballantyne the first time we tried this, which is there is indeed a second answer. So the reason there's a second answer is that Q represents an expression that evaluates the list AB. And there are infinitely many expressions. So if I were to do a run star instead of a run 2, this would diverge. Okay? If I wanted to make sure that there was only a unique answer, I could just put a quote in front of the logic variable. And then sure enough, the only answer would be AB. Okay? So this is a very subtle thing, but we can play around with expressions of various sorts. And just like we were playing around with appendo and running it differently, we can run append in scheme. We can treat scheme's append now as a relation, even though it's just normally a function. So through the relational interpreter, we inherit this relational behavior even for functional programs. So function is a way to turn functions, to treat functions as relations, basically. But we can go beyond the standard behavior of appendo style behavior. And instead, we can do things like put the logic variables inside the code for the definition of append. So here I've replaced car of L with Q. And if I run this expression, now I've performed some program synthesis where the system has figured out that if you had car of L in this position, that would give the right behavior to append. Okay. And then I'll show you one last thing. I'll change my color scheme real quick. Okay. So if you take this sort of interpreter and you make it much faster, thanks to Greg Rosenblatt, for example. Then you can put this beautiful Swift GUI that I created on top of it, and you end up with this little tool that we call Barliman. And you can see in Barliman we have a skeleton of a program. So if we kind of zoom in there, you can see that we have the outline of a scheme function definition. Okay, we're defining some function, we don't know the name. So whatever you see a comma and a capital letter, that's a logic variable or a hole. So we're defining some unknown function, we don't know the name, we don't know the arguments to the function, we don't know the body to the function. So these, we've got a little bit of a skeleton. If I wanted to, I could fill it out some more. So I could say we have a function called append. So I can type in, I could type in as much as I want, give it more structure, but I don't have to give it really any structure. And now what I can do is test-driven development, okay? But real test-driven development, because I can do something like say, if I append the empty list to the empty list, I should get the empty list, okay? So I can fill in a particular test, the input and the expected value, and then I can see sort of a best guess, okay? So the Barliman interpreter, relational interpreter, figured out, okay, from that example, it looks like you're trying to define a function called append. It's variadic maybe, who knows? And it's just going to return the empty list because that was the result of the example we gave. Okay, so that's consistent with the example, but that's not really what I'm thinking. So I'll give it another example. So how about A and B should be AB. Okay, now think about it a little more. Okay, so now in order to make that work, so okay, you're defining append, it takes two arguments, I don't know what the names of the arguments are, and I'm going to have an if in this case, and we'll have the null test, so it's guessing more of the structure, but you can still see it's over-specializing to AB, for example, and it hasn't figured out the recursion. So let's add another test. There are various ways to do this, but in this case I'm just doing pure example-based programming. So, okay, C appended to D is CD. So at this point, it prevents the over-specialization, and you can see that now we're talking cons and cars. Still hasn't guessed the recursion. So let's give it one more example. So append of EF to GH. Okay, and this one might take a minute. Let's see if it can figure out the recursion. Now, one point in time, I calculate, okay, so it took 14 and a half seconds, and so it figured out the recursion at this point. Now, we still don't have any variable names, so if I wanted to, I could do things like say, actually, I want the variables to be L and S, okay? And so, I could do things like give it specific variable names or hints or things like that. And so now you can see that when it synthesized the program, it used the variable names I specified. Okay. Now, there are a couple of interesting things here to note, I think. So one is we now have a program synthesis system that can slowly do things like synthesize recursive scheme programs by example. And the interesting thing to me about that isn't so much that we have a synthesis program system. There are many synthesis systems today, but it's that we got the synthesis system automatically by just writing an interpreter as a relation. So we just committed ourselves fully to this relational style, and the output is a synthesis system because we can put logic variables anywhere we want. Now, making it fast enough to do this small example took some work. As Ken Divig says, optimization is the art of cheating without being caught. So we had to do a lot of cheating without being caught. So this The tweaked interpreter is still a relation. You can still put logic variables anywhere you want, but we've had to hand code some things to make it faster in cases where we can take advantage of structure. Right now, there's a whole bunch of other work going on by different people in different groups to try to make the systems much faster still. Things like staged evaluation, supercompilation, using types like the miniKanren work from the St. Petersburg group and so forth, to try to be able to reason better about these programs, to be able to make it more efficient, to require less human work to try to tweak it. So I think you see both the promise and the challenges. So the promise is you can write your program as a relation, and you can encode the semantics directly. We have different versions of miniKanren that support different types of logics and things like nominal logic programming from Andy Pitts' group. So we have alpha Kanren. You can implement those sorts of rules like capture avoiding substitution and so forth. And there's higher order miniKanren now. There's lambda Kanren and so forth. And there's lots of work on trying to be clever about efficiency related things. But there's still a lot of work to be done. I'll also say that it took us about 13 years of work to get to the point where we could do this. Okay, and this is a tough road to climb. But if you think about how long it took the notion of lambda to get from lambda calculus in the 1930s into Java, it took something like 70 years from the theoretical work to getting it into Java. So yes, it's taken a while. It will take more time. However, I'm optimistic. If you think of the longer-term time scale, I think that's the way the time scale in which some of these things work. Also, more recently, there's been a lot of progress in things like neural guided search or using LLMs to guide search, and sort of the other styles of AI. So this is symbolic AI, sort of a traditional search-based symbolic AI and constraint solving. But now we have all sorts of generative AI and neural networks and so forth that work very well. So that's a challenge also, is to tie these sorts of things together. And then there's also lots of other things like, what happens when you tie dependent types to a language like miniKanren? Because it turns out dependent types and relational programming have a lot of similarities. In both cases, you're sort of encoding this logic, and in full versions, it might even be undecidable. So it feels like that's a similar sort of thing, and in fact, I'm interested in encoding Idris, doing something with Idris, for example, in miniKanren to see where that goes. Okay, I think we've got about 18 minutes left. I could certainly show more, but I think this is kind of the nice broad overview, and I know that we have people here, maybe people online, who are experienced miniKanren programmers, or at least have seen probably most or all of this before. And so I'm curious if anyone would like to ask any questions, or say anything in response to this, or propose directions in which this might go, or talk about some experiments that they've made maybe that are a little bit different than what I've shown. Yeah.
So it's very thrilling to see this.
Yes, microphone, please. Yeah. Well.
All right, VC from used to from Indiana University.
Okay, another former. We have in the room at least 3 PhDs under 4 PhDs. Oh, well, a new PhD in training. So yeah, we have 4 generations of Dan Friedman's miniKanren students in this room.
So you mentioned there was some fiddling to make this work, this Append to be generated. And I'm wondering, so this kind of improvement, did you do it on, say, miniKanren level or a lower level?
Okay. Yeah, so in order to make the Barlaman version of the relational interpreter work, there were 2 things we had to do. So one was we had to extend the language of the interpreter over the very simple interpreter to be able to handle things like append nicely. So that that was more like just writing a nice interpreter and being very, very careful. And we also had to add some new constraints to miniKanren to handle certain things so we could get the shadowing right. And Scheme's kind of a tricky language to handle in some ways because you're allowed to shadow any of the operations and redefine how lambda works and all that. So we wanted to be able to handle all those aspects. So it required some very careful representation of the programs and introducing some special constraints. We had disk quality constraints, absento constraints, symbolo, numbero constraints that aren't in, for example, the Reason Schemer books. Although maybe we'll be able to put those into another edition. Oh, who knows? But it required some extra constraints. That was part of it. It also required, having a faster version of miniKanren. So we have a very simple version of miniKanren, like the microKanren work. A very nice, simple version of miniKanren. It's easy to implement. But on the other hand, if you really want to do something that's going to take a lot of computational power, you want the fastest implementation you can get. So the faster miniKanren implementation has various optimizations, or at least more efficient data structures for representing substitution and things like that. And then the last part of it was Greg Rosenblatt made a whole bunch of hand tweaks to both the miniKanren language in the search and to the interpreter. And if you haven't looked at the code, so if you look at the, you can find the Barlaman code on GitHub. And if you go into the Barlaman, let's see, Barlaman Coco, Barlaman MK, and RHEL interp, and then if you look at the interp, that SCM, there's a parser up front. But then when you actually get to the real interpreter, you'll notice that, okay, so here's the interpreter. And you can see that there's some weirdnesses here. So first of all, there's a let star. Okay, so Greg is mixing scheme code and miniKanren code. Then he's also walking variables, and then he does things like check in the lookup code if the environment is sufficiently ground where you can just call regular scheme lookup, that type of thing. And then also you can see he's got this weird cond $ depth first search, and then he's got these hand tweaks of like how much of a priority it should be. And then the other thing that's really important is that when it comes to procedure application is tricky because it turns out that you have to make at least 3 recursive calls for a procedure application. You have to evaluate the operator, the operand, and then the body of the lambda, the closure you get back. So you have to do at least 3 recursive calls, and the order in which you do those recursive calls is dependent, the optimal order is dependent on the groundness of the arguments. So there is no one right way to do it. It's sort of like I was talking about with the append example, where when you have multiple recursive calls, there's no optimal way to do it. So what Greg does is he does a dynamic check on the groundness of the different arguments and then dynamically reorders the recursive calls at runtime to try to get better ordering. But it's not perfect. So that's the sort of thing where hopefully you could do it statically. Hopefully the programmer maybe could give hints. There are a whole bunch of ways that you can imagine trying to solve that problem. This is a partial solution, but it also, you can tell, it requires a lot of like low-level hand coding, so it would be good to make that automatic, and also it'd be good to make it static. And also these numbers, Greg basically just made those up and tweaked those by hand. It would be good if we could have maybe machine learning or profiling or things like that to help us generate those sorts of numbers automatically. And also, I could tell, there's work by Nadaman and Michael Ballantyne, for example, on staging the relational interpreters. There's also work by St. Petersburg group on supercompilation and so forth. There's a whole bunch of techniques we're using to try to figure out if we can get better performance. Also, Lisa Zhang and her collaborators have a paper on neural guided search. That's another approach. We've been doing some work with Rob Zinkoff and Michael Ballantyne on using n-gram guided search on a small corpus of scheme code and so forth. So there are a whole bunch of ways that you might go. And we're not using types here that could help. But it's tricky right now. So So Greg did find that there are a couple tweaks that help a lot. The application, the two ones that I understand that have a big impact are checking groundness of the environment to see if you can do a regular scheme lookup instead of lookup-o. That's a huge win. And then the other one is dynamically reordering the recursive calls to application. That's a huge win. So if you could only implement two things, those would probably be the ones to do.
That's really awesome. Thank you. An additional question is, so I have this feeling that anything that is relational is slow. I mean, if you look at that equal, maybe in a functional programming language, it happens instantly, right? But here we are at least doing unification, which is linear or worse. Right?
That's right.
So I'm thinking maybe if we try to move the work from the relational world to the functional world, it'd be faster somehow. And for example, in this particular example of this interpreter, maybe if we move beta and alpha just to, or in higher order unification, so it happens in scheme rather than miniKanren, maybe it could help.
I think you're right. That's something we seem to have learned, that anything we could do, say in scheme or whatever host language we have, versus doing it as a relation, we should do that when we can tell we can do it, right? And so that's why Greg uses lookup instead of lookup-o when he can, or you really can use like an assoc or askew or something in scheme, which is, I don't know, 10,000 times faster or something. I mean, it's much, much faster. So the work that Jason and Michael Ballantyne are doing with the optimizing compiler, that I think that's also part of the idea. And also things like, I know Jason, you've looked into removing occurs checks for unification. So occurs check for unification is very expensive. So it's not just the unification itself, it's the occurs check also. And there are times where you can guarantee that the occurs check can't be violated. And also one of the optimizations in faster miniKanren is that in certain cases when you introduce a new fresh variable and then immediately unify it before you hit a cond, you can actually just mutate a cell that contains the value instead of having to extend the substitution and all these other things. So there are times where you can avoid putting things in substitutions. And also we're not garbage collecting our substitutions in terms of we're not doing environment trimming. So once something gets added to the substitution, it never goes away. There are problems like that as well. So I think there's a whole lot we could do, but you're right. The best thing is to just not do something as a relation if it's not absolutely necessary. And if you look at the Mercury language, the Mercury language takes a different approach where you write something as a relation and then it gets compiled to individual functions, like kind of regular functional programming with different modes depending on the arguments. So that's another thing we could do is like if we actually are just running in one direction and we don't have compound terms that contain logic variables in them, then we could do a Mercury approach and we compile to functions that go in different directions. So I think there's a whole lot we could do. I think it's still wide open.
Thank you.
Thank you.
Hi. Walter Schulze, Go miniKanren.
Go miniKanren.
Yes, go. I was wondering again about these recursive calls and the order. Like if you have a simple example, maybe just a calculator with plus where you have to go down both sides, right?
Yeah.
And you mentioned this groundness check. What is that?
Okay.
We can take it offline if it's too complicated.
Sure.
That's
Well,
fine.
I will. It's such an important thing. I will try to, kind of show you real quickly.
Yeah, I'm pretty sure it's going to be tough.
Yeah. I mean,
sorry.
I can lead. I mean, it's not that hard to understand, I think, but it is. It's important here. So, let's see if I can find the app case. If you look through this code, you will find. Okay, here's the closure, same length. I don't know if I'll find it. Let's see. Okay, eval application, here it is. Okay, here's the eval application. So you can see this code is kind of, it's not super long, but this isn't just 3 recursive calls. There's a lot more going on, okay? To me, the canonical example, by the way, of the reordering is if you write an interpreter that has to handle cons recursively. Because if you have cons of E1, E2, then you have to evaluate E1, and you have to evaluate E2, and then you have to put the results together. Well, you can put the results together first, but you still have a recursive call on the first argument to cons and the second argument to cons. And I can write very simple examples where the call to cons and the expected output value are such that with one ordering of the recursions, you'll get failure, and another ordering, you'll get an infinite loop when there is no answer. And whichever ordering you pick for the recursion, I can trivially, swap the 2 positions of the input cons expression and the output expected pair that would defeat your ordering. So you either have to figure out a more sophisticated way, to do the conjunction, and there are approaches, by the way. There was work on Andorra Prolog, for example. Andorra Prolog, there was a lot of research on how to do parallel conjunction, or how to evaluate things separately, or do dependency analyses. I mean, so people have done a lot of work on trying to understand this problem and how to try to do better. But there are cases where it's all entangled and it's tricky to make it work. So you can see in this application case. Now, first of all, this is general application where you don't know how many arguments you are. Okay, so it's a little more complicated. But you can imagine already, as soon as you have, some function applied to an argument, you already have 3 recursive calls, it turns out. So here you can see what Greg did versus the standard application. And here he's got let values, he's getting suffixes of the rands. Okay, list split ground. So he's doing an analysis at runtime to find where are the ground values or the ground expressions. And I think you have to go through this code and maybe talk to Greg Rosenblatt about it as well. But it's a little bit tricky. And the key part is, he can reorder things based on groundness. And the part of the problem, though, with this approach, there are a couple of problems. So first of all, there's a lot of overhead because you have to do all these checks at runtime for groundness and walking things and so forth. It's expensive. So you just have overhead. Even if you have the right ordering, you have a lot of overhead. But another problem is, the groundness rules are a little complicated. And one of the things you'll notice with Barlaman is there are times where you can make your program a little more ground. You can add structure, and you would think, oh, this is really going to speed things up. But actually, it slows it down enormously. And the reason is you've changed the groundness of one of the arguments to an application, and now everything's reordered. All the applications are ordered differently. So it's not like this is guaranteeing an optimal ordering. It's more like a heuristic, and it works sometimes, and sometimes it actually does the wrong thing, and it actually makes your program slower. The St. Petersburg group has done a lot of work on trying to use structural recursion properties on the operation, on the arguments, so they can statically guarantee that certain orderings work well and things like that. Peter Lozov in particular has done work on this with Dmitry Buchalov's group. So that's something to look at as well. So if you have types, if you have static knowledge, if you know that you have a primitive recursive relation, things like that, then you can do much better. And in fact, you can do things statically as well. So this is an area where I think we're very naive. We figured out some things work, and we've got this one cool program, which is like the relational interpreter, which is very powerful. So we now know that we can do these things, which I think people hadn't suspected in the past. But trying to make this efficient is going to require, like Edward Commett likes to say, throwing all the computer science at it. We've thrown a tiny bit of computer science at it. We're going to have to throw a lot more at it. Yeah.
Thank you.
Thank you. Okay. I think we have time for one more question, if there are any. Otherwise, I think it's about time for the break and to get ready for the next session. Okay, I think this is a good time in, thank you very much.